Karnaugh maps are very useful when optimizing functions that are incompletely specified. This means that given a truth table for a function, there are some outputs that will be either 1 or 0, but the functionality overall of the final circuit doesn't really depend upon the outputs for the given inputs. Karnaugh maps, given don't cares as outputs for these cases, can be used to optimize circuits effectively. Let's go through a few examples. In this first example, we're going to show a 4-input variable K-map that has several outputs specified as don't care, specifically here and here with the x's for W. Input variables D, E, F, and G. So now let's create our table. Since we have 4 input variables, we need 16 entries in our final map, similar to the table. And then we count using gray code format. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. So, going right down the list, let's remove these arrows here. We can start with entry 0, 0, 0, 0. The output is 0 for W. Given inputs 0, 0, 0, 1, the output is 1. Input 0, 0, 1, 0, the output is 0. And input 0, 0, 1, 1, the output is 1 again. Input 0, 1, 0, 0, input is 1. Input pattern 0, 1, 0, 1, we have an output X. This means that we don't care what the output is for this particular point. It can be 1, it can be 0, we don't care. Whatever we choose to set there is just fine for the functionality of the circuit, but we can choose it such that it optimizes our Boolean network and our digital circuit that much better. Our next entry, 0, 1, 1, 0, is 1. Next entry, 0, 1, 1, 1, is again a don't care. So we're going to specify that as a don't care again. So now 1, 0, 0, 0 is a 0. Whoops, incorrect location. So 1, 0, 1, 0, 0, 0 is a 0. 1, 0, 0, 1 is a 0. 1, 0, 1, 0 outputs a 0. 1, 0, 1, 1 outputs 0 again. Next, 1, 1, 0, 0 outputs a 1. 1, 1, 0, 1 outputs a 0. 1, 1, 1, 0 outputs a 1. And finally, 1, 1, 1, 1 outputs a 0. And so we now have a Karnaugh map with don't care entries. So because we don't care whether the x's are 1s or 0s, this gives us a new rule for grouping. So we must group all 1s, and we may optionally group don't cares but not needed. So if it is good for us to group the don't cares, and we can form a larger group by using the x's, then we may form a group with them. but if not, then we don't have to use them. And we'll see a few examples here. So let's look here. What are the largest groups? I see a group of 2 1s here that we can circle, but this is not the largest group that we can form for these 2 1s, right? We can form a group using these 2 1s with the 2 don't cares for a group of 4 1s. And this still gives the correct output for W because we don't care what the x values are. They can be 0, they can be 1. So let's go ahead and create a large group using the x's. W equals, what is the term given for this group? Well, for these 2 rows, D is 0, so D prime. For these 2 columns, G is 1, so G. Next, we have another group here that we can find for 4 1s, potentially. Probably the most optimal group that we can choose is to go around the edge by grouping these 2 1s with these 2 1s over here. By wrapping around the edge, we are gathering the last 4 1s into a single group. It is possible to say, well, we only want these 2, or we could just group these 2 1s by themselves in their own separate group, but this will increase the number of groups unnecessarily. We'll have AND gates that are appearing out in our final circuit that are unnecessary, so let's leave those off. One other possible group that we could use is this one, but then this one and this one would be missed. And because we've already covered all the ones with these 2 groups, there's no need to add that third group, or a third group in general. So this second group, what is it? Well, we know here E is equal to 1, and we know for these 2 columns, G is equal to 0, G prime. So now that we have a Boolean algebra expression, we can create our digital circuit. Let's do that now. D, E, F, and G. And then we can create our inverted variables. We have 2 of them, D and G. Let's label these here as D prime and G prime. And then we can draw our sum of products form. AND gates, D prime G, and EG prime. And these pipe to an OR gate. And then we develop an output W. Very clearly looking here, it does not require us to consider the value of F. F is a don't care. So we could actually, in this instance, completely drop the variable F input from this circuit and optimize it that way. Our next example here, we have again 4 variables. Let's set up the K-map. I, J, K, and L. We have 4 variables, so let's create our map with 16 entries. And then count in gray code format. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And we can just go right down the line. Remember, using the counting format, we'll use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Once you get used to counting in this order, it will be very quick and easy to just go down the list and enter one variable after another. So let's label this again, I, J, K, L. Like so. Show the count again, gray code count. 0, 0, 0, 1, 1, 1, 1, 0. And now let's go down the line. 1, 0, 1, 0. We covered this group of 4. Next we'll go with this group of 4. 1, 1, 0, 0. Let's use this group next. X, 0, 1, 0. And then finally this group, X, 0, 0. Oops, apologies. We need to use this group next, X, 0, 1, 0. X, 0, 1, 0. Then finally, the last 4, X, 0, 0, 0. This one is a bit tricky. First of all, we can look at this one here, and probably the largest group that we can form is a group of 2. Because we can't wrap around the edge to any other ones and we can't turn any quarters. So let's just grab that first. No other possible groups can be made with that. Now we need to look at the last 3 ones, and we need to group them all somehow that is quick, efficient, and with the minimal number of groups possible. We can use the don't cares, but we don't have to use them all. So what's the trick? We need to wrap around the edge, but because it's a group that has the possibility of going around the horizontal edge and the left and right edge and the top and bottom edge, we can use both. So let's do that. This wraps around the top. So we have a group of 2 that wraps around the top, which wraps around the left and right with this other group here. Notice that we are grouping 1 and X in the top left and the bottom left. Correct? And it covers our final remaining 3 ones when we combine it into one group. Therefore, our optimal implementation is 2 groups. So W equals I prime J ANDed with K prime, ORed with, so we need L prime, and J prime. J prime, L prime, like so. Now that we have two terms for our two groups, we can build the digital logic circuit. Let's do that now. I, J, K, L. And we need I prime, K prime, J prime, and L prime. So we need all four inputs inverted. So I prime inversion. Oops, let's make that a little bit neater. K prime inverted and L prime inverted. So we need two AND gates, I prime, J, and K prime. And then we need a second AND gate, J prime and L prime. These output to a NOR, like so, and we get our output W. So question, what if we wanted to use only NAND gates for the two levels of the network? Well, we could invert the output of this AND gate and the input of this OR gate. Two inversions equate to a null operation, so this does not affect the operation of the circuit. We can do that here and here as well, the output of the NAND gate and the input of the OR gate. And a double inversion is a null operation. It's basically buffering. So we've lost no information. We have not changed the functionality. But all the logic gates are NAND gates. Interestingly enough, for this two-level network here. So when I refer to the two-level network, it seems to discount the inverters here. What is interesting in digital circuit design is that these inverted values very often are available to us. So it is always good to take advantage of them when they are provided. So another example with don't care terms that we should look at is using for variable function f format using sigma notation. So using sigma notation, we can see that f equals summation of this set of terms here. Now the four variables are labeled A, B, C, and D, but it is sometimes possible to see this notation, M0, M1, M2, M3, up to M15. So it's good to at least be aware of it. So what does this come out looking like when we convert it? Well, let's redraw the K-map. With ones, zeros, and don't care terms. Gray code counting again. So M1 must be 1. So we're looking here again at where the 1's are. F is equal to when we have M1, so we have this entry as a 1. Let's fill that in. M3 is a 1, so let's fill that in. M7, let's fill this in. M11, right here. So we can place a 1 here. And then M15, right here. So we have a 1 again. Now for the don't cares. M0 first, so we can place an X. M2, it appears here, so let's place an X here. And then M5, which is here, so we can place an X there. All other entries are 0. We'll fill those in now. Now that we've filled in our K-map, we can start grouping items. For these ones here at the bottom, we can group with the full column for CD. Let's do that immediately because there are no other possible groups that can combine with these two ones at the bottom. This makes it a little bit easier. And now we have only a single one left to group. So what is the simplest group? There are two possibilities that are equally valid. They both give the same number of logic gates. Let's pick this group here. We could pick one other group, which would be equally valid in terms of complexity. It would just be different. The only reason that we can have this difference is that we don't care what the values are for 3 of these entries. So can you find what the other group is that's possible? If you considered boxing this group, then you would be correct. So you can pick that one or this horizontal group for this row at the top. Either or is fine. Notice that we must cover all ones. And we may optionally cover X's or don't cares. So let's implement our for variable function as a Boolean expression. F is equal to CD for this row, for this column, and then for the top row, or A prime, B prime. And we have our Boolean expression. Digital logic circuit. Need all 4 input variables, and we invert 2 of them. Place these in. These inverters need to be here. And now we need 2 AND gates. Let's start with CD. And A prime, B prime rather. Now we can OR these 2 terms together. And we get our output F. 7 logic gates, or not 7 logic gates, 5 logic gates, including the NOT gates. Now we have another example of a Karnaugh map with don't care terms. Let's go ahead and prepare it now. Notice that the variables are not specified. So let's just create some dummy variable names. We can call it I, J, K, and L. When the variables are not specified, you can choose your own variable names. Just remember to be consistent. So we have our K map. So let's fill this in now. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. For the ones, and now for the don't cares listed here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All other entries are 0. Now this one is a little bit interesting because some of these x's aren't needed, perhaps all of them. Let's look at the largest group of ones that include this one in the corner. Notice that even wrapping around the edge, it has no neighbors that are 1 or x's. There's one probably to the corner, but you cannot make diagonal groups. So we must have a singleton here. Let's pick another group. For this one up here, it has a maximum power of 2 group, including 2 ones, just like this. We cannot increase the length at all, so we're stuck with a maximally sized group of 2 ones. Now, let's look at these 2 ones here. These 2 ones, what is the largest possible group? Well, it would be nice if we could do something like this, but that is not a power of 2. So let's just go ahead and box the 4. Now, here comes the $25 question. Do the don't cares add anything to our simplification process? Do they help us in any way? The answer is no. If we try boxing any more groups in, if we try to create any more groups, then we are going to create them unnecessarily because all ones are covered. We don't need to cover any of the don't care instances. So let's go ahead and create our final output. F equals, let's look at the very small singleton group, I prime, J prime, K prime, L prime. That covers this one in the corner. Let's look at this pair. We have I equal to 0, so I prime and K and L must be 1, so KL. Finally, for this larger group, we have these last two columns, k equal to 1, and for these two rows, j equals to 1. So we will OR with jk. Let's build the digital circuit. I, j, k, l, I prime, j prime, k prime, l prime. Let's label our variables as well so we know what we're connecting to. And then the primed outputs from the inverters. So now we need 3 AND gates. The first one requires 4 inputs from all the inverted variables, so I prime, j prime, k prime, and l prime. Next one, I prime, k, and l. Finally, j and k. These all pipe into an OR gate. This gives us our final output F for this K-map with don't cares. So this concludes our series of 4 examples of K-maps using don't cares.